Welcome to Study Unit 2, Lecture 3. So Lectures 3 and 4 will focus on capacitors, which are used extensively in power electronics. Capacitors are generally represented by one of these two symbols here, which is analogous to the parallel plates, which form the basis of a capacitor's operation. The unit of measurement for capacitors is farads and is represented with an F. Capacitors can either be non-polarized, in which case they're represented by this symmetric symbol here. Polarized capacitors have a positive and a negative terminal and are usually represented by a symbol similar to this one over here, although there are other variations. In power electronics, there are broadly two types of capacitors. There are capacitors which have a liquid and solid electrolyte, and there are capacitors which make use of a plastic film to create the dielectric layer between the plates of the capacitor. At the end of Lecture 4, ceramic and mica capacitors will also be briefly discussed, but they don't find extensive use in power electronics. The primary function of a capacitor is to store electric charge. The charge is actually stored between these two plates in the electric field, which is set up by the potential across the two plates. The amount of charge stored, Q, is given by the capacitance multiplied by the voltage across the terminals of the capacitor. The charge can also be represented by the integral of the current through the capacitor with respect to time. This is particularly important when considering AC signals through a capacitor. It should be seen here that the capacitance can be expressed in terms of the capacitance, the voltage, and the current without needing to take the amount of charge stored into account. This can be done by equating these two sides of the equation and solving for the current. Here the current is expressed as the capacitance multiplied by the change in voltage with respect to time across a capacitor. The value of the capacitor is a function of the geometry of the capacitor as well as the electrical properties of the dielectric between the parallel plates or parallel surfaces in the capacitor. Fundamentally, a capacitor consists of two conducting plates separated by some distance W with a dielectric which fills in the space between the plates. Fundamentally, the capacitance is given by the total area of the plates divided by the distance between the plates multiplied by a relative dielectric constant and epsilon 0, which is the dielectric constant for a vacuum. The reason the dielectric constant is expressed as the dielectric constant for a vacuum multiplied by some relative dielectric constant is because depending on what material is used between the plates, this relative value can change, whereas this epsilon 0 will stay constant. By changing the relative dielectric constant, the properties of the capacitance can be changed. The purpose of the dielectric is to change the effective spacing between the two parallel plates in the capacitor. This is accomplished in two ways. The dielectric can change the force experienced between the two plates as well as the relative electric field which is created between the two plates. If two electrons in free space are considered, the force which draws these two electrons together or apart is given by this equation here, which is the charge of the two electrons divided by 4 pi multiplied by epsilon 0 multiplied by the radius squared of the distance between the two electrons. This force equation here is for electrons in a vacuum. When the electrons are in a substance or some material, then there is a new relative dielectric constant which must be taken into account when determining the force between the two electrons. This expression is very similar to the expression for vacuum, but with the inclusion of a new relative constant which is determined by the material itself. Simplifying the relative force equation gives the zero force divided by the relative dielectric constant. This means that the relative dielectric constant in effect reduces the force experienced between the two electrons. In a similar fashion, the electric field around an electron in a vacuum is given by this equation here. Once again, notice the dielectric constant for vacuum. If that electron is in some material or some substance, then there is a relative electric field created by the electron, and thus a relative dielectric constant needs to be factored in. In a fashion similar to how the relative dielectric constant reduces the force between the particles, the relative dielectric constant also reduces the electric field strength between the two charged particles. Shown here is the equivalent AC model of the capacitor. This model consists of the actual capacitance, an effective series inductance, and an effective series resistance. The AC behavior of the capacitor is modeled by having the capacitance as the real part of a complex impedance and a complex resistance. For this model shown here, RD and CD are not too important as they are specific to electrolytic capacitors. The resonant frequency of the capacitor omega R is given by 1 over the square root of the series inductor and the actual capacitance of the device. The impedance of the capacitor Z is given by the series resistance, or ESR, minus J over omega CR, which represents the complex part of the impedance. The service life of a capacitor is characterized by how long various parameters of the capacitor will remain within some or other specification. When one of these parameters falls out of spec, then the capacitor is said to be degrading. There are various parameters of the capacitor that can degrade, such as the capacitance itself, the leakage current, the dissipation factor of the capacitor, and so on. Manufacturers will specify what are healthy parameters for the capacitor to stay within spec, and this way the designer can choose the applicable capacitor for a certain application. In general, the operating environment as well as the circuit conditions under which the capacitor operates will have an effect on the lifetime of the device. So under normal operating conditions, the capacitor will have a typical lifetime bathtub curve as shown here, where there will be some failures with a very high failure rate initially. This is the infant mortality phase. During phase 2 is where most of the capacitors from a manufacturing batch will operate if operating within spec, and when these come out of spec, this will be the service lifetime of the device. As devices exit the service lifetime, the failure rate will increase as the capacitors start to degrade because they basically just get too old. This is important to take into account when designing systems which need to operate for extended periods of times over many years. There are several ways to increase the lifespan of a capacitor. The first is to operate the capacitor at a lower ambient temperature. The second is to decrease the ripple current or ripple voltage through or across the capacitor. The third way is to lower the operating voltage across the terminals of the device relative to the maximum rated voltage. And lastly, the higher the AC frequency across the device, the lower the load will be on the device, and thus the lifetime of the device will be extended. A common failure mode in capacitors is when the applied voltage across the device terminals exceeds the rated voltage of the device. When this high voltage is applied, there will be defective areas inside the dielectric which will experience abnormally high electrical fields. In these high electrical fields, arcing will start to happen, which will further damage the dielectric. Electrolyte oxide capacitors and plastic film dielectric capacitors do however have self-healing properties which will allow the capacitor to continue operating even after some overvoltage damage has occurred. Depending on the construction of the capacitor, the self-healing properties of the capacitor will be different. In the case of electrolytic capacitors, the high field strengths will first manifest as defects in the dielectric. However, these high voltages will also allow for more oxide to grow and repair the damage in the capacitor. Thus, this will allow the electrolytic capacitor to self-heal. In metallized plastic film capacitors, the high field strengths effectively destroy the defective area, and this region will no longer manifest with a very high electric field, thus protecting the rest of the device from the overvoltage failure. Liquid, or sometimes called organic, solid, metal oxide dielectric capacitors are manufactured by depositing aluminium and tantalum oxides onto foil. The aluminium and tantalum oxides allow for the direction of current to be controlled. In this capacitor construction, there will be a layer of aluminium foil which will have aluminium oxide etched onto it, forming the anode. The paper dielectric soaked with electrolyte will be combined with a piece of foil which has aluminium oxide etched onto it to form the cathode. This structure can then be either stacked or wrapped to form the capacitor, which is eventually packaged. An important aspect of this type of capacitor construction is that it is unipolar. What this means is that the voltage at the anode must be higher than the voltage at the cathode. If the voltage is reversed or exceeded, then additional oxide will start to form on the cathode. This will cause more conduction through the cathode, which leads to heating and the formation of gas inside the capacitor, which will release the magic smoke, which is often seen when capacitors blow up. Another property of capacitors is that an applied DC voltage will cause some leakage current to flow in the capacitor. Shown here is a graph of what typically happens with time. Once the capacitor has a voltage across its terminals, there will be some high leakage current, but as time progresses over minutes, this leakage current will decrease. The lower the leakage current, generally the higher the quality of the capacitor. A capacitor which is operated outside of its operational parameters, or one that has exceeded its service life, will see an increase in this leakage current, which will decrease the performance of the device. An advantage of liquid oxide dielectric capacitors is that the leakage current is quite low. Like all devices, a capacitor does have a power rating. A capacitor which operates in an AC environment will have some AC ripple on the current and voltage across the terminals of the device. The peak RMS value of this ripple cannot exceed the maximum rating for the device, or the device will start to degrade or experience catastrophic failure. The maximum ripple current which is allowable across the device terminals is the square root of the maximum power dissipation divided by the series resistance of the capacitor. This effective series resistance is a function of temperature and frequency. Thus, the maximum allowable ripple current is also a function of temperature and frequency. As mentioned, the reliability of the capacitor device can be greatly extended and the service life greatly extended by not exceeding the environmental parameters recommended for that device. This is particularly true for liquid aluminum oxide capacitors, where stress reduction is key to maximizing the service life of the device. Ripple current is the dominant factor determining the service life of liquid aluminum oxide capacitors. If the ripple current, along with the operating voltage and temperature, is kept within spec, then liquid aluminum oxide capacitors can give decent service life. In general, liquid capacitors have a shorter lifetime than corresponding solid capacitors. Also, solid aluminum capacitors tend to have a better lifetime than solid tantalum types. In general, solid capacitor types have a high capacitance per unit volume because of a high permittivity present in the tantalum used in these solid capacitors. Solid type capacitors are also more resilient to variations caused by temperature. And finally, a solid electrolyte is stable and won't evaporate with time, as is the case for a liquid electrolyte. And that concludes this lecture. Lecture 4 will carry on with capacitors.